Imagine that the ocean you see today is nowhere close to the ocean that first appeared on Earth. The water splashing around your feet on a beach right now was once scalding steam surrounding a planet that held not a single drop of life. How old is the ocean, really? And what existed before even one drop of water appeared on this planet? Today we are going to descend not just through kilometers of depth, but through 4.5 billion years. Every meter we sink will carry us hundreds of millions of years further back, through layers of water and through layers of time, all the way to a point where the ocean did not exist at all. Welcome to the longest journey you could possibly imagine, a journey to the bottom of time itself. Scientists still debate the exact age of the ocean. Some estimates put it at 4,300,000,000 years, while others shift that number by another 1 to 200 million years in either direction. But even trying to picture a span of time that size breaks our intuition. If we compress the entire history of the ocean into a single hour, all of written human history, every kingdom, every war, every book, would take up less than 1/100th of a second on that clock. To put the scale of deep time another way, if a single second on our imaginary clock represented roughly 1,250,000 years, then everything you personally have ever experienced, your entire lifetime, would flash by in far less time than it takes to blink. 4.5 billion years ago, Earth was not a blue planet. It was a molten ball of scorching rock without a single drop of liquid water on its surface. Surface temperatures exceeded 1,000 degrees. No ocean could have survived those conditions, since any water would have instantly turned to vapor. But the young Earth had a secret weapon, an atmosphere thick with water vapor, carbon dioxide, and other gases pouring out from the planet's interior through volcanic eruptions that never seemed to stop. Slowly, over millions of years, the planet's surface began to cool, and once temperatures dropped low enough for the water vapor in the atmosphere to condense, what may have been the longest rainfall in the history of the solar system began. Rain likely fell without pause for hundreds of thousands, perhaps even millions of years, filling the first low points and basins of the planet with water. There's another theory that adds to this picture. Some of that water may have arrived on icy comets and asteroids that bombarded the young planet during the first few 100 million years of its existence. It is possible that both sources, the volcanic one from within and the cosmic one from beyond, combined to create the planet's first ocean. That first ocean looked nothing like the one we know today. Its water was far more acidic due to the enormous amount of dissolved carbon dioxide. The sky above it was probably not blue, but a reddish-orange because of the atmosphere's composition. And the planet's surface kept shuddering under constant volcanic eruptions and the impacts of remaining asteroids. And yet this was the beginning, the start of a story that, billions of years later, would lead to every fish, every whale, and every drop of water you have ever drunk. There is indirect evidence that liquid water appeared on the planet even earlier than long assumed. By studying tiny zircon crystals more than 4 billion years old, found in Western Australia, scientists discovered chemical traces pointing to interaction with liquid water. That means water may have existed almost as soon as Earth itself finished forming, which shortens the window during which the planet was completely dry, far more than previously thought. To grasp the scale of today's ocean, it covers more than 70% of the planet's surface and holds about 97% of all the water on Earth, including the water flowing through rivers, locked inside glaciers, and forming the clouds above your head right now. If all of the planet's water were spread evenly across its surface, that layer would be roughly 2.5 kilometers deep. The first ocean also looked nothing like today's in size and shape. Continents, in any familiar sense, did not yet exist. There were only the first small fragments of solid crust rising above an otherwise continuous water surface. Perhaps there was so little land back then that if a person could have looked at the planet from space, they would have seen an almost solid water world, dotted with dark, volcanic islands. Before we descend to the origins of life, there is one more upheaval the early ocean endured. According to one theory, roughly 700 to 600 million years ago, the planet very nearly froze over completely, with ice possibly stretching from the poles all the way to the equator, turning Earth into something resembling a giant snowball. This hypothesis is known as snowball Earth. Life during this period is thought to have survived only in scattered pockets of open water, perhaps near volcanic vents on the seafloor, where the planet's inner heat pushed through the icy shell above. Let us descend deeper to where, on the ocean floor, in a darkness that sunlight never reaches, one of the most important events in the history of the universe took place: the origin of life itself. Life is believed to have first sparked at hydrothermal vents, cracks on the ocean floor where hot, mineral-rich water pours out. These vents created unique chemical conditions, a steady flow of energy, a mineral-rich environment, and shelter from harsh cosmic radiation that was not yet blocked by a full ozone layer. The earliest forms of life were incredibly simple, single-celled microorganisms that needed no oxygen at all to survive. In fact, oxygen at the concentrations we know today would have been lethally toxic to them. For billions of years, these simple, single-celled organisms were the only inhabitants of the planet. Think about that for a moment. For most of Earth's history, life amounted to nothing more than single-celled microorganisms floating in the ocean. No plants, no animals, not even a hint of anything more complex than a single cell. Then, roughly 2.5 billion years ago, an event occurred that is sometimes called the Great Oxidation. Certain microorganisms called cyanobacteria evolved the ability to use sunlight to produce energy through photosynthesis, and oxygen was the byproduct of that process. At first, oxygen was a deadly poison to most life forms that existed at the time. It essentially poisoned the oceans, triggering one of the earliest mass extinctions in the planet's history, wiping out organisms for which oxygen was toxic. But at the same time, the Great Oxidation opened the door for an entirely new kind of life, organisms capable of using oxygen to generate far more energy. That very evolutionary path would eventually lead to complex multicellular organisms, and ultimately to you, watching this video right now. Evidence of this ancient era survives to this day in the form of stromatolites, layered rock structures built up by colonies of cyanobacteria over thousands of years. Some modern stromatolites, for example in Shark Bay in Western Australia, are still growing today, remaining among the few living witnesses of an age when life on the planet consisted entirely of single-celled organisms. Another crucial step happened roughly 1 to 1.5 billion years before the Cambrian period. Some single-celled organisms formed symbiotic partnerships that likely gave rise to the first cells with a nucleus, known as eukaryotes. From cells like these, hundreds of millions of years later, every complex multicellular form of life would eventually develop, including sponges, jellyfish, and ultimately every other group of animals. Shortly before this explosion of diversity, in the several tens of millions of years leading up to it, the oceans were already home to strange organisms known as the Ediacaran biota, soft-bodied creatures with flat or leaf-like shapes, lacking shells, eyes, or limbs in any familiar sense. Many of them look so unlike anything that came afterward that paleontologists still debate whether some of these organisms were animals at all in the conventional sense, or represented a separate evolutionary dead end that vanished entirely by the start of the Cambrian period. One more leap through time, and we arrive roughly 540 million years ago, in the period scientists call the Cambrian. Before this point, life on Earth remained mostly simple, single-celled organisms alongside a handful of primitive multicellular forms. But over a relatively short stretch of time, just a few tens of millions of years by geological standards, the ocean exploded with a diversity of life the planet had never seen before. This event is known as the Cambrian explosion. Suddenly, the oceans filled with creatures bearing hard shells, complex eyes, limbs for moving across the seafloor, and jaws for hunting. The ancestors of modern arthropods and mollusks appeared, along with the distant ancestors of vertebrate animals, including every fish, amphibian, reptile, bird, and mammal alive today, humans included. One of the most recognizable creatures of this era was Anomalocaris, a predator about 1 meter long with enormous compound eyes and a pair of grasping appendages near its mouth. By Cambrian standards, this was an absolute monster, sitting at the top of a food chain where most other creatures measured only a few centimeters. Why did life suddenly accelerate its diversity at this particular moment? Scientists have several theories: rising oxygen levels in the atmosphere and ocean, an evolutionary arms race between predators and prey in which hard shells on some species forced others to develop new forms of defense or attack, and an accumulation of genetic changes that suddenly unlocked countless new paths of development. Alongside Anomalocaris, Cambrian seas were home to trilobites, segmented creatures with hard shells that proved so successful they survived on the planet for more than 250 million years, outlasting several mass extinctions along the way. One of the strangest creatures of this era was Hallucigenia, a tiny animal with a row of spikes along its back and several pairs of thin legs, an appearance so puzzling that early researchers spent decades reconstructing it completely upside down. The Cambrian explosion established the basic body plans for nearly every animal group alive on Earth today. Everything that followed in evolution has essentially been variations on themes first tested in Cambrian oceans. One of the richest sites for studying this era is the Burgess Shale in Canada, where rare conditions preserved not just hard shells, but soft tissue impressions of creatures that lived more than 500 million years ago. This single location allowed paleontologists to reconstruct the appearance of dozens of strange organisms, some so unlike anything alive today that scientists had to create entirely new classification groups just for them. Shortly after the Cambrian explosion, the first true predators with hard internal skeletons appeared in the oceans, ancestors of vertebrates that vaguely resembled small, jawless fish. Jaws, as we know them, did not exist yet. These ancient fish filtered water or scraped food off the seafloor with a toothless, funnel-shaped mouth. Only tens of millions of years later would fish develop true jaws, an invention that every vertebrate animal on the planet, including humans, would eventually inherit. We continue our descent through time and arrive in the age of the dinosaurs, or rather, its underwater counterpart. While dinosaurs ruled the land, the oceans belonged to an entirely different group of animals, marine reptiles. Mosasaurs were among the most fearsome predators of Mesozoic seas. Some species reached lengths of more than 15 meters, longer than a modern city bus. They had powerful jaws lined with multiple rows of teeth, and hunted almost anything that crossed their path, including other marine reptiles. Plesiosaurs looked entirely different, with a long neck, a compact body, and 4 powerful flippers instead of fins. Some plesiosaur species likely hunted by slowly approaching prey and then striking with a sudden lunge of that long neck, much like a snake. It is important to understand that despite their outward resemblance to modern reptiles, neither mosasaurs nor plesiosaurs were dinosaurs in the strict scientific sense. They were separate branches of reptile evolution that independently adapted to ocean life, returning to the water after their ancestors had once crawled onto land. While these giants ruled the open ocean, life along the coasts and shallow seas was thriving in its own way. Ammonites, relatives of modern nautiluses, existed in an incredible range of shapes and sizes, with some species reaching shells more than 2 meters across. Beyond the familiar coiled spiral, ammonites also included genuine evolutionary experiments. Species with nearly straight, elongated shells or shells twisted into irregular, almost chaotic patterns, which still leaves paleontologists debating exactly how such creatures moved and hunted. This age of marine reptile dominance lasted tens of millions of years, right up until an event that changed everything. Sharks were also present throughout this entire era, quietly surviving in the background while mosasaurs and plesiosaurs claimed most of the attention. Sharks as a group are far older than either of these reptile lineages, with ancestors stretching back hundreds of millions of years before the Mesozoic even began. Their basic body plan proved so effective that it has barely changed across all that time, making sharks one of the most successful and enduring designs in the entire history of life on Earth. Worth mentioning is another group of marine reptiles from this era, ichthyosaurs, which appeared even earlier than mosasaurs and looked strikingly similar to modern dolphins, despite having no close relation to them whatsoever. This is one of the most striking examples of convergent evolution in the planet's history. 2 completely different kinds of animals, separated by tens of millions of years, independently arriving at almost the same streamlined body shape, because that shape turned out to be the most efficient for fast swimming through water. Ichthyosaurs went extinct earlier than mosasaurs and plesiosaurs, for reasons that remain unclear, though changing climate and competition for food with other predators, including those same mosasaurs occupying a similar ecological niche, likely played a role. Let us descend even deeper, to layers that hold the traces of the greatest catastrophes in the planet's history. Long before the Permian extinction, roughly 445 million years ago, the ocean had already endured one of the first truly massive catastrophes, the Ordovician extinction. It is thought to have been triggered by sudden cooling and a subsequent ice age, which caused sea levels to drop and destroyed many of the shallow water ecosystems where the greatest concentration of life existed at the time. Around 85% of all marine species died out, making this one of the largest extinctions in the planet's history, and it happened before a single living creature had ever set foot on land. The largest mass extinction in Earth's history happened roughly 252 million years ago, at the end of the Permian period, long before the age of dinosaurs. Scientists sometimes call it the Great Dying. Depending on the estimate, somewhere between 90 and 96% of all marine species on the planet vanished. The cause appears to have been colossal volcanic eruptions across what is now Siberia, continuing for hundreds of thousands of years. These eruptions released enormous amounts of carbon dioxide and other compounds into the atmosphere, driving sharp climate warming, ocean acidification, and a catastrophic collapse in oxygen levels in the water. By some accounts, the oceans of that time took on a purple hue, caused by the massive proliferation of certain bacteria that thrived in oxygen-free, toxic conditions that killed off nearly everything else. This phenomenon became known as the Purple Seas. More than 150 million years after the Great Dying, already in the age of dinosaurs, another catastrophic event occurred, an asteroid impact on the Yucatan Peninsula roughly 66 million years ago. This event wiped out not only land-dwelling dinosaurs, but also marine reptiles, the mosasaurs and plesiosaurs that had ruled the oceans for tens of millions of years. The impact threw enormous amounts of dust and soot into the atmosphere, blocking sunlight for months, possibly even years. This sharply slowed photosynthesis, both on land and in the ocean itself, where tiny plankton formed the base of nearly the entire food chain. The collapse of that foundation was one of the main reasons the extinction reached even marine creatures living far from the impact site. But every single time, after every catastrophe, life in the ocean found a way to recover. Surviving species filled the empty niches, evolution ran new experiments, and within millions of years after each extinction, the ocean bloomed again with new diversity unlike anything that came before. The Permian extinction was far from the only catastrophe of this scale in the ocean's history. Scientists generally identify 5 major mass extinctions over the past half-billion years, and at least 3 of them were driven primarily by changes within the ocean itself: falling oxygen levels, sharp swings in water temperature, or acidification. After recovering from each of these events, the ocean typically emerged with an entirely new lineup of dominant species that had previously played only minor roles. We are nearly back at the surface, back in our own time. After the marine reptiles went extinct, another group of predators claimed the top of the ocean food chain for tens of millions of years: sharks. And one of the most impressive among them was Megalodon. This giant predator, which lived roughly from 23 million to 3.5 million years ago, reached lengths of around 15 to 18 meters, and its bite is considered by scientists to be among the most powerful of any vertebrate animal in history. Megalodon disappeared long before humans existed, likely due to a cooling climate, declining numbers of large prey such as whales, and competition from newer predators, including the ancestors of modern orcas. After the extinction of the marine reptiles, ocean ecosystems gradually reorganized around a new group of animals: mammals that returned to the water. The ancestors of modern whales were once land-dwelling creatures, distantly resembling small, hoofed predators. Over millions of years, their bodies transformed beyond recognition. Limbs turned into flippers, hind legs nearly disappeared, and nostrils migrated to the top of the head, becoming a blowhole. Sometimes the ocean delivers discoveries that flip scientific assumptions upside down. In 1938, South African fishermen caught a large, strange-looking fish that scientists immediately identified as a coelacanth, a creature believed to have gone extinct alongside the dinosaurs more than 60 million years earlier. It turned out this ancient lineage of fish had quietly continued living in deep waters the entire time, unnoticed by science. This discovery remains one of the most striking reminders of just how incomplete our knowledge of the ocean still is today. Today, the ocean is home to an animal larger than any that has ever existed on the planet: the blue whale. Its heart is roughly the size of a small car, and its call is the loudest sound produced by any living creature on Earth, capable of traveling thousands of kilometers underwater. Even though the Great Oxidation happened billions of years ago, the ocean's role as an oxygen producer never disappeared. It simply changed form. Today, depending on the estimate, somewhere around half or even more than half of all the oxygen in the planet's atmosphere is produced by tiny marine algae and phytoplankton, not by forests on land as many people assume. Every other breath you take literally owes its existence to the ocean. The ocean also functions as the planet's enormous climate pump, thanks to a system of deep water currents sometimes called the global ocean conveyor belt. Warm water moves from the equator toward the poles along the surface, cools, grows denser, and sinks into the depths, then slowly makes its way back through deeper layers, a journey that can take more than 1,000 years to complete a single cycle. This current system redistributes heat across the entire planet and shapes the climate of whole continents. But perhaps the most astonishing thing about the modern ocean is how little we actually know about it. Scientists estimate that humanity has explored in detail less than 1/5 of the ocean floor's total area. Roughly 240,000 marine species have been formally described so far, but some estimates suggest the real number of species living in the ocean could reach as high as 2 million, meaning the overwhelming majority of our neighbors sharing this ocean have not even been named yet. Deep-sea ecosystems, existing without a single ray of sunlight, still deliver new species discoveries almost every year. Sailors told legends for centuries about giant squid, sea monsters capable of dragging a ship to the bottom. And it was only in 2004 that scientists first managed to photograph a living giant squid in its natural habitat, confirming that behind the myth stood a very real, if extremely rare, creature. The same holds true for the strange creatures living at hydrothermal vents on the sea floor, the very same kind of place where, according to one theory, life itself first began billions of years ago. Between the sunlit surface and total darkness below lies what is known as the twilight zone, a layer of water where sunlight still penetrates, but not nearly enough for photosynthesis. This layer may hold more living biomass than any other part of the ocean, and the overwhelming majority of its inhabitants produce their own light through bioluminescence, whether for hunting, camouflage, or attracting a mate in a world where the sun is never quite bright enough. When a whale dies and its body sinks to the ocean floor, it becomes the foundation of an entire temporary ecosystem known as a whale fall. Such a carcass can feed deep-sea creatures for decades, first large scavengers, then smaller organisms that break down soft tissue, and finally specialized worms capable of feeding on the fats stored within the whale's bones. For many deep-sea species, a carcass like this is a rare oasis of abundant food in a world where food is normally in desperately short supply. The circle that began its scorching vents on the floor of the first ocean has, in a sense, closed. Even today, in the darkest and most inaccessible corners of the planet, creatures survive whose ancestors witnessed the very earliest days of the ocean's existence. The deepest point in the world's ocean is the Mariana Trench in the Pacific, with a depth exceeding 10,900 meters. If Mount Everest were placed at the bottom of that trench, its peak would still sit more than 2 kilometers below the surface of the water. Pressure at that depth exceeds surface atmospheric pressure by more than 1,000 times, roughly equivalent to the weight of a small car pressing down on every square centimeter of a body. And yet even there, in that extreme environment, scientists continue to find living organisms adapted to conditions that seem utterly incompatible with life. At some of these same hydrothermal vents, the very kind of place where, according to one theory, life first began billions of years ago, giant tube worms still live today, growing more than 2 meters long. These creatures have no mouth and no digestive system at all. Instead, they live in symbiosis with bacteria housed inside their own bodies, which convert the chemicals pouring out of the vent into nutrients. This is one of the few examples known to science of life that is completely independent of sunlight at every stage of its food chain. Humanity first reached the bottom of that trench only in 1960, when the bathyscaphe Trieste, carrying 2 people aboard, touched the deepest point on the planet. It would take more than 50 years before anyone returned. Even today, only a couple dozen people in history have ever made that descent, a reminder that exploring the depths of our own planet has, for most of history, been a harder task than traveling into space. We have risen through 4.5 billion years, from scorching steam on a young planet to blue whales singing in the depths of the modern ocean. Every drop of water you have ever seen in your life made this incredible journey. But here is the paradox. The very same ocean that survived asteroid impacts, monstrous volcanic eruptions, and at least 5 mass extinctions is now changing faster than it has at any point in the past several tens of millions of years. Water temperatures are rising, acidity is increasing due to absorbed carbon dioxide, And some ecosystems, including coral reefs, are collapsing within the span of a single human generation. Coral reefs, which took tens of thousands of years to form, and today provide a home for roughly a quarter of all marine species, have already lost a significant share of their area due to rising water temperatures, and by some projections could lose most of what remains within a single generation if conditions do not change. Bleaching events, where corals expel the colorful algae living inside their tissue and turn ghostly white, have become dramatically more frequent in recent decades, and reefs now need far more time to recover between one bleaching event and the next than they used to. Over the past several decades, the ocean itself has absorbed more than 90% of the excess heat the planet has accumulated from greenhouse gases, effectively acting as a shield that has slowed warming on land. But that comes at a cost, since this absorbed heat is altering currents, reducing oxygen levels in the water, and fueling more frequent and more powerful storms. At the same time, millions of tons of plastic waste enter the ocean every year, breaking down into microscopic particles that scientists now find in even the deepest and most remote corners of the planet, including that same Mariana Trench, and increasingly inside the bodies of the very marine creatures whose ancestors have called this ocean home for hundreds of millions of years. On top of that, runoff from fertilizers and other nutrients flowing off the land triggers explosive algae growth in coastal waters. And when that algae dies and decomposes, the decomposition process consumes nearly all the dissolved oxygen in the water, creating what are known as dead zones, where almost nothing can survive. The world's ocean today contains several hundred of these zones, and the number keeps growing. The ocean survived everything the planet threw at it across billions of years of its existence. The real question is whether it can survive us. 4.5 billion years compressed into roughly half an hour of watching, and yet the ocean outside your window right now carries every single one of those years inside it, in its chemistry, in its currents, and in the countless generations of creatures whose descendants are still swimming through it today.